What did past environments look like if they are constantly changing?
Uh, that's, you know, basically in geology and sedimentology and in other fields, we use rock record proxies, or what I call, indicators recorded in sedimentary rocks, particularly of past events. So, as you're aware, you need to have an understanding of how events that are important in the geologic record are recorded in sediments and sedimentary rocks. So you need to have an understanding of the processes that operate on the surface of the earth that lead to particular facies or kind of bodies of sediment. So it's that old saying, in some ways, the present is a key to the past. So I'd say a young geologist, a student, needs to consider either in the field or, and preferably, through the literature, is how professionals interpret bodies of sediment based on what is happening today at the Earth's surface. Now, that doesn't mean that there aren't some sedimentary deposits that may not reflect what's happening on the Earth today. I think of, for example, snowball Earth, the theory of massive glaciation. We don't have that on Earth today. It hasn't happened, over hundreds of millions of years. But, many of the same kind of processes that are responsible for glaciation are recorded in the rocks that people like Paul Hoffman used to interpret the snowball Earth theory. He was he did a lot of his work in South Africa and in Namibia, where they have these beautiful sedimentary rock sequences that record the change from an interglacial world back in the Paleozoic or the Neoproterozoic, I think, into a full glacial world. And, geologists have wondered, for example, is it possible to have a repeat of a set of conditions like that? And probably the answer is no, because the atmosphere is different now and the distribution of continents on the surface of the planet is different. So we deal with a unique kind of period in geologic history where we would not get glaciation on that scale. But that isn't to say that you can't get glaciation on the scale of the ice ages, the Pleistocene glaciations, where a third of the planet, of the terrestrial planet, was covered by ice. To me, that's incredible, And, I'm basically trained as a glacial geologist. So in British Columbia, we have a lot of sedimentary deposits that record these periods of glaciation, of continental glaciation. And coming back to your question, and I know I'm rambling, but I tend to do that, we can see these deposits, these tills and these outwash deposits, and look at modern glaciers and modern landforms, geomorphic features, and make some reasonable interpretations of what's happened in the past. And that's it's almost a four-dimensional exercise. You need the three spatial dimensions, and then you need time. And in sedimentology and in geology in general, that's why time is so important, because it's as you mentioned, it's kind of an evolutionary thing. Things do change over time, and we don't look for, we look for snapshots in time, but we also want to see how those snapshots kind of play out in terms of a video, a time video. And it's every geologist's dream to transpose themselves back in time to see how this actually happened. But we make reasonable interpretations based on modern environments and modern landforms. And I would add, just as a final comment, that it's not just the sedimentary rock record, when you're dealing with young events in Earth history, and by young, I'll explain what I mean. But when you're dealing with young events, you want to also interpret landforms because landforms are associated with sediment. So it's a two component exercise. You want to understand what's beneath landforms. And again, returning to the issue of glacial geology, if we see a drumlin, these nice kind of whaleback ridges in the landscape, we can make a reasonable interpretation of what underlies them. It's going to be probably a glacial deposit, maybe some outwash, but they're clues they're part of the puzzle as to how you interpret the past. And then, coming back to the issue of time, it's very important. I mean, a major field of geology in general is geochronology. And traditionally, it's been based on the fossil record. So when you're dealing with old events, you use a fossil record. So you have biostratigraphy. Biostratigraphy is a relative age dating tool, but we have other ways of calibrating the biostratigraphic record using things like ash deposits that you can, I don't know if you're aware of this, but you can actually date volcanic ashes through the radiometric techniques of uranium, thorium, and fission track. And so all this wonderful work has been done to kind of put numbers on the biostratigraphic record, put numbers on evolution. It's so cool.